So, a quick example of an autocorrelation process, the autocorrelation of a square pulse, which is a convolution of the pulse with itself, okay, is essentially the autocorrelation of a square pulse with itself is a triangular pulse. I think we discussed this in one of the earlier lectures. If you aren't convinced, you want to possibly program this on your favorite computer language, MATLAB or Python or whatever, right? A Gaussian pulse autocorrelated with itself yields another Gaussian pulse. It is therefore no surprise that tau, the denominator here, which is a measure of the full width at half max of the pulse, delta tau p, is related to linearly to delta tau a, which is the width of the autocorrelation. 1.44, 1.414, which is the square root of 2, okay, times the full width at half max of the pulse turns out to be the full width at half max of the autocorrelation signal. This is linear autocorrelation. So, that is a thumb rule that you can employ as an experimenter. Secant hyperbolic, if that is the pulse form you think your laser has, it's the multiplicative factor is 1.54. So, these regular pulses all seem to have this feature. Now, second order autocorrelation works this way. That is something which we figured out, right? And this is the implementation. I just wanted to have an intermediate recap of how to do higher order autocorrelation. So, getting past that, why is autocorrelation working at all? We want to step back and examine, in the case of laser pulses, this very fundamental principle of how am I getting some information about the pulse itself. Where is the function and where is the window, where is the gate, right? How am I able to visualize, how am I able to slice this very fast signal in time and get information about it? Obviously, there must be some gate hidden somewhere, whether it is linear, in which case we do not have a gate which is shorter than the pulse itself, or it could be one of the nonlinear orders, second or third order autocorrelation, employing a crystal. Well, look at the signal that we are measuring in the autocorrelation process. What we call the signal is a variation of something with respect to the delay tau, and that invariably involved the product I of t times I of t minus tau. Yes, the rest of it was a DC term. The signal that we had earlier had 3 pieces. It was E square of t plus E square of t minus tau plus a term which was something proportional to the intensity or the field. Here let me write it in terms of intensities, I of t times I of t minus tau. It is this term, the interference term, which gave us information about the pulse. Because this is a product, I can segregate this scenario where a copy of the pulse I of t is delayed with respect to another copy, which is I of t minus tau, both of which are interfering to produce the delay varying signal. When I have this product, look at what is happening here. There are 3 regions, a region left of 0 on the scale. In this region, the pulse to the right has 0 amplitude. So, I of t times I of t minus tau produces a 0 to the left of 0, correct? Whereas, to the right of where we have marked tau, The pulse to the left, which is here, which I am now shading in orange, its amplitude turns out to be 0 for all delay times which are greater than the point marked tau on this time axis. In all these points, the orange pulses envelope goes to 0. So, a contribution to this product arises only from the overlapping region, which is the yellow marked rising falling pulse over here. So, that is the basic notion of autocorrelation. We have taken two pieces of this pulse, multiplied them and gotten information only from the two tails. Now, as the pulses start coming closer, they start overlapping each other and information comes increasingly from the central regions of the pulse itself. So, this is the output. We need to figure out a way to invert this information to figure out the individual pulse shapes. That is the whole challenge of this problem. The simplest quantity to figure out here is the width of the autocorrelation signal and correlate it to the width of the pulse, assuming that the time varying signal is Gaussian or secant hyperbolic, making an assumption based on whatever knowledge. Like one can show using a reasonable mathematical formalism that these lasers which produce femtosecond pulses will produce pulses which have a secant hyperbolic time variation. I know this from the physics of the laser, but that is of course a very ideal scenario. We cannot sort of be sure that the pulses are a clean secant hyperbolic. One needs to fundamentally measure them out in reality. But I have some knowledge that it is like a Gaussian. You could have assumed that this is a square pulse, does not matter. Make the simplifying assumption that the laser produces square pulses, make two copies, do the autocorrelation, you get a triangular pulse, you measure its FWHM, get a measure of its FWHM and get a measure of what you thought was the square pulse. It may have been, you may have overshot or oversimplified matters by assuming that the pulse produced by the laser is a square pulse in time. But that is okay, we have to live with it, and that is the best that we can do by doing this very simple naive retrieval problem. I retrieved a width based on some assumed knowledge. I have to do better if I want to get much better detailed knowledge. In that sense, autocorrelation we must realize is a gating process. It gates two pieces of a signal depending upon how much overlap there is in time of these two copies of the pulse, right. Now that we have an idea that we can produce a gate using interference, let us take one step further. What is the step further? We want E of t which amounts to measuring I of t and phi of t, or equivalently we want E of omega which amounts to measuring S of omega and phi of omega, right. See, we are going to combine these two things in a very clever way, and please try to absorb this as nicely as you can. We want information on time scales, and what do we have on the other hand? We have a technique where we have E of t and a delayed copy E of t minus tau. And from this we know how to produce the second order autocorrelation signal, which is Fourier related to the spectrum. So, we are kind of inching towards a much better solution, it seems. We have to piece these together to get a good idea of things, right. Now, we can have more information than we currently do, because with the current information it seems I can get an idea of I of t and have very little idea of phi of t. We have not said anything about getting the phase out. So, we need additional info, that is where we are heading, and we are heading towards, we also know that the 1D retrieval problem mathematically is not something we can solve. So, I can't solve in 1D, but that is basically lack of information. A 2D problem could have a solution, it in fact does. But to put all this together, where do I get that extra dimension from? Of course, this is easier said than done. What we want to do is the following. We know now that interferometry or interference produces a gate signal g of t. I have the unknown function e of t. This is the function I desire to know. Actually, in this case, I do not have a simple gate. That is the whole problem with pulse metrology, that there is no God given gate. G of t is something we need to create, and all pulse metrology techniques vary from one another on how we produce the gate, and since we have a knowledge of how we produce the gate, how we retrieve the information for that particular scenario. All pulse metrology techniques, advanced ones, more advanced than autocorrelation, essentially rely on the understanding of the gate function. For now, do not worry about what the gate function is and how we are going to produce it. Assume that we have a gate function which is like the white curve here, the white box. It's a keyhole function. It's just a slit in time. If we have such a slit under our control, then we can through the interference process produce a signal which multiplies this slit function with the entire Gaussian, right, and the detector could measure something which is about the area under this curve. So, I will be able to get a slice out. If I can sweep the gate all over and as a function of delay get the signal out, if I know the gate very well, I can figure out what E of t is. That seems to be the idea over here, right. So, we can figure out a spectrogram of the waveform if I go a step further and I employ a gate, and from the gated region measure the spectrum of the pulse only in the gated region. I produce the spectrum of the pulse in this region centered about tau. Okay. So, I basically measure omega of tau and then start sweeping tau all through. What am I getting a measure of? I am getting a measure of the instantaneous frequency inside the pulse, right. Recall we had omega t is omega naught minus d phi by dt. So, therefore, if I get a measure of omega of t, except for maybe a constant of integration which may or may not play a role, I simply have to integrate this out to get a phi of t, this frequency function, right. There may be convolutions and the such involved due to the finite width of the gate, but that is another matter, we can still deal with that. So, this is going to be the basis of doing pulse metrology, a gated spectrum measurement or the measurement of a spectrogram of a waveform. But this is of course looks very sophisticated for optics, but this is applied like everywhere in signal processing. techniques like wavelet transform do actually this sort of a thing. Okay, a musical score is a time varying waveform. There you play frequencies as a function of time, right? But then musical instruments are not really just single frequency. A note could be a combination of frequencies and so on. I am not an expert on that, but basically music is also a fine example of this as an analog, right? So now that technique is going to take us through. I am not going to elaborate on these advanced spectrogrammatic techniques in this lecture. We will look at it forward. Now basically I just want to point out that since we are talking about doing higher order autocorrelation measurements, such as using a second harmonic crystal, we should be aware as an aside about geometrical distortions in autocorrelation. In order to achieve phase matching, the two beams need to cross the crystal at an angle, right? So the two pulses, if you wish, are incident on this crystal at a tilted angle, like that, right? So this effect actually causes a range of delays to occur at a given amount of time, and some amount of geometrical smearing tends to take place on account of this, because this animation is the best way to see it. One can write this down mathematically nicely. So watch this again. Both the pulses propagate, and when they intersect in the crystal, essentially the leading edge of one part of the beam mixes with the intermediate or trailing edge of another copy of the pulse. Okay, so this can lead to some amount of geometrical smearing out. In this case, the two centers of the beam are interfering, whereas in any other intermediate case, I cannot pause the simulation here, various other regions were interfering. In other words, in this region of the crystal, pulse 1 arrives earlier than pulse 2. In the central region, pulse 1 and 2 arrive at the same time. In the third region, pulse 1 arrives later than the other. This is not something we intended by design in this form of autocorrelator. The whole point being that a detector cannot distinguish between all these guys. You place a lens, collect all the signal, and then make a measurement. So therefore, the angle at which the pulses are incident introduces a certain smearing out or an uncertainty or an error bar in tau, the delay variable, owing to geometry. But we can turn this into an advantage, as we will see a little later. Now, a single shot autocorrelator does exactly that. What it does is it exploits the fact that here pulse 1's leading edge, that is, it arrives earlier, meets with the trailing edge of pulse 2, or is it the other way around? Work it out. But pulse 1 arrives earlier here than pulse 2. So here is the 0 of delay is at the center. There is, say, minus tau going away from the center to the top, and plus tau going away from the top to the bottom of this crystal. So now the whole idea of doing a single shot autocorrelation is, instead of a single detector, here place a pixelated detector, a camera, and capture the second harmonic generation on a camera. Okay. Use the pixels of a detector. Remember, whether you have one photodiode or a camera with, say, 512 pixels by 512 pixels, for example, all of these are going to give you a signal which is essentially integrating over all of time. It really does not matter that a photodiode produces a pulse on the oscilloscope is inconsequential for you. You are just going to take either the peak to peak of the pulse or the area under the curve or whatever. The time there has no significance in this problem. Instead, here if you have a camera with different pixels, you can produce a histogram on these pixels which will look effectively like this. It's actually going to be a 2D signal. So if you calibrate it, the width of this histogram is going to give you a width of this pulse in a single shot second order autocorrelator. Why? Because in a single shot autocorrelator, as a function of delay, at 0 delay, if it's a well behaved pulse, maximum signal will come from 0 of delay, because that is where the temporal overlap between the two pulses is the best. So here too, where the overlap of the most strongest regions of these two pulses is present, you are no doubt getting the highest signal. Of course, my sketch is not very symmetric with respect to this, but you get the idea. So you can therefore eliminate your delay line in performing this sort of a measurement with a short or a long pulse in a second harmonic crystal. Of course, the point being, if you have a very long pulse, you need a much larger crystalline detector which may or may not be at your disposal. So this technique works best for shorter pulses, relatively shorter pulses. So that is a single shot autocorrelator. It's faster and everything else, right? So now when you do a single shot autocorrelation, we ought to worry about whether the second harmonic generation that's happening in the crystal is phase matched over the entire bandwidth of the pulse. So S of omega is kind of like that. What if phase matching was very good only for a smaller region of the pulse? What if? Maybe, why not? Because it involves k is 2 pi over lambda, right? Then there is a problem, because then the pulse that you are measuring is effectively only this much. You are slicing off things in the frequency domain, so your pulse will appear longer in the spectral domain. It acts like a filter. It acts like a combination of a high and a low pass filter, or something like a notch filter. It will in the spectral domain, so it will distort things in the time domain. So that's something one ought to verify. But phase matching, remember, depends, or phase mismatch accumulates with length of the crystal, right? So a thick crystal often results in a smaller phase matching bandwidth. A thinner crystal means a broader phase matching bandwidth typically. Okay. So now a thick crystal will generate a narrow second harmonic signal and it cannot be used, whereas a thin crystal is therefore required in doing second order autocorrelation. So the crystal thickness could be like 100 microns, which also makes this element a bit fragile, or it could even be thinner. If you want to measure a much broader band of pulse, you actually want a thinner crystal, which also means that your overall signal will also go down. It also goes down with crystal length as by the same factor of sinc square, right? Remember, the phase matching term was sinc square delta k times L, that is your second harmonic signal. So if delta k is large, you want a smaller L so that your signal does not die down. Which is essentially the behavior of the sinc square function. I am deliberately doing this a bit quickly. You can read at leisure more about this. Okay. So second harmonic generation bandwidth also plays a role. Therefore, the second harmonic crystal bandwidth must exceed the bandwidth of the pulse. This notion thereby comes about very importantly, but there is also a bit of a nasty trade-off, because thinner crystal, as I said, lower signal but greater bandwidth, as may be required for the metrology of much shorter and shorter pulses, right. We can also do a third order autocorrelation if you so wish, right. Here we can use the optical Kerr effect to do third order autocorrelation, right. We can do that by means of a polarization gating. Okay, here essentially what we do is the following. I am giving you just a case study or an example of a third order autocorrelation. Up to this part, it is straightforward and boring. You just produce delay. We have E of t, we have E of t minus tau. Okay. So now here you rotate the polarization of these two pulses which had identical polarization, okay, by an amount of 45 degrees. Here you introduce a polarizer, okay. Now make these two interact in a glass, in a nonlinear medium, which could even be glass. You need essentially optical Kerr effect to start taking place. Here you have another polarizing beam splitter which essentially reflects off light of the same polarization. It does not allow it to pass through. So it is an analyzer which is crossed with respect to this polarizer as far as this detector is concerned. So if I did not have E of t at all, this detector would see no signal, right. But here is the point. Now you come in with the second pulse whose polarization is 45 degrees with respect to that of the incident pulse. Owing to the optical Kerr effect, okay, you produce a signal at the same omega as that of the pulse, epsilon naught chi 3 E square E. Okay. So now in the presence of this test field, you can take any one of these to be the test field. In the presence of the other field, basically the polarization of this incoming pulse goes from being purely vertical to having some amount of ellipticity. Now this analyzing beam splitter will now be able to reflect off this. So you have introduced a gate based on polarization, and that is a third order effect because it is a chi 3 effect. Now scan the delay and produce a third order autocorrelation signal. It is a very simple implementation. So this could be a piece of glass, or for example at optical near infrared wavelengths, a popular third order nonlinear medium such as carbon disulfide, which has pretty high, relatively high chi 3 values, can be used to produce a polarization gate. Okay. So if you have a shorter reference pulse available somehow from a laser emitting multiple pulses from the same seed laser, which can be a certain scenario in some laboratories, you can do some frequency generation to use one of the shorter pulses as a gating pulse. You measure the autocorrelation of this pulse, characterize your gate, and use that to measure the details of an unknown pulse. For example, this unknown pulse may have propagated through a plasma. You can do spectral sort of interferometry by cross correlating the known pulse, that is the gate pulse, with respect to the unknown pulse in a some frequency generating crystal, and use a slow detector and get temporal information. So you can do metrology. You can, by measuring pulses, you can also measure the pulse itself or processes that happen on time scales of the pulse of interest. So, if you may be working with maybe laser material processing, you want to know how this process takes place in time, right. So, you can start sort of making movies or some kind of, you can do 2 pulse measurements for it. You can have a gating or a probe pulse. I mean, you can take the pulse that goes through your medium, use a reference pulse, do some measurements. You can play tricks like that, right. So, now I spoke about interferometric or fringe resolved autocorrelation pretty early. So, that is another important aspect of doing autocorrelation measurements. So, there is a whole lot of autocorrelation physics that one can be aware of in these scenarios. I am not going to go through the math of interferometric autocorrelation. I will leave these in the notes for you to work this out as to how the interferometric autocorrelation second order signal is produced, right. The interesting term, as I have always maintained, is the cross term in this entire interferogram signal which we measure. So, we will I will just leave the math with you for you to work out. As I said, an interferometric autocorrelation or any second order autocorrelation essentially, and in this case an interferometric autocorrelation brings about a basic 1:8 contrast that is involved in pulse metrology. Okay, so a comparison of interferometric and intensity autocorrelation shows us that interferometric technique captures the fringe substructure in it. As a consequence, it acts as a calibration for the delay scale in this case. Okay, so each of these fringes would correspond to one optical cycle tau. So, if an optical cycle is 2.7 femtoseconds as it is for 800 nanometers, then from determining the FWHM I can simply count off the number of fringes in the span over here and figure out what the pulse width is going to be. So, it is a sort of self calibrating technique. And for autocorrelation we can build up a table. When you know the shape of your pulse, if you measure the autocorrelation delta tau from the autocorrelation, you can figure out the delta tau of the pulse, the delta t of the pulse. So, from these two quantities will be easily nicely related for various pulses. It is Gaussian, secant hyperbolic, this is a bi-exponential sort of pulse and so on and so forth. We can work out the math for this. Okay. So, we will examine in the next lecture the problems that we have with autocorrelation traces of pulses and motivate why we need more advanced pulse metrology techniques. Okay. With that, I will close for today and take any questions if there are. We can pause the recording.